Hello, and thank you for joining Maplesoft's Virtual User Summit. My name is Shola Slough, Technical Communications Specialist at Maplesoft, and I'm your host for this presentation. The presenters for this session are available in the Communication Lounge from 1:30 to 2 p.m. for a live chat on the day of the event. So please head over to the Communication Lounge and select the appropriate scheduled chat for this presentation to ask any questions you may have. If you are viewing a recording at any other time and have questions, please leave them on the message board in the Communication Lounge and a Maplesoft representative will get back to you. This session is titled Advances in Mathematical Computation from Maplesoft. Not only do many people use Maple to advance their research in a wide variety of fields, but Maplesoft itself is involved in advanced research projects for mathematical computation. In this session, you'll hear about some of the latest progress by Maplesoft and its academic partners in parametric polynomial systems, polynomial arithmetic, differential-algebraic equations, and physics computation. Let me now introduce our presenters. Dr. Edgardo Cheb-Terrab is Team Lead, Physics, Differential Equations, and Mathematical Functions at Maplesoft. He received his PhD in theoretical physics from the Federal University of Rio de Janeiro and went on to become the head of the theoretical physics department at the State University of Rio de Janeiro. He currently works for Maplesoft, concurrent with periods at the University of Waterloo, the University of British Columbia, and Simon Fraser University. His main areas of interest are quantum field theory, general relativity, and education. He has developed many innovative algorithms in Maple to support both research and education. He is the main author of the world-leading ODE and PDE symbolic solvers in Maple, as well as the groundbreaking physics package. Our second presenter, Dr. Juergen Gerhard, holds a PhD from the University of Paderborn, Germany. He has been with Maplesoft since 2003 and is currently its Director of Research. His primary area of interest is symbolic computation and its applications in engineering. He coordinates research and consulting projects in these areas at Maplesoft. Together with Joachim von Zurgatten, Juergen is the co-author of Modern Computer Algebra, one of the most popular textbooks in the field.
Hello, my name is Edgardo Cheb-Terrab, and I would like to talk about the functionality available in the Maple system for doing algebraic computations in physics. So, first of all, why computers? Physicists do their algebraic computations with paper and pencil, and they are very successful in doing so. So why would we use computer algebra in the first place? Well, I think that there are several advantages in user computers for algebraic computations. So first of all, you can concentrate more on the ideas instead of all the details of the algebraic manipulations. You can extend your results in easy ways. You can change the values of parameters. You can add equations to your system. You can change the form of the potential in your problems, and so on. You can explore the mathematics around your problem in very easy ways. For example, you can plot, you can compute series, you can check for special values for some special functions that maybe enter your problem. And not less important, you can share your results with your colleagues in a way that the results are reproducible, because you can send a worksheet and your colleagues can reproduce all your computations and even change part of these computations and send the worksheet back to you. And in this way, you can exchange about a problem in a very productive way. So if it is so good, why is that computer algebra were not being used by physicists more? And the reason, I think, is that there was a severe representation problem with regards to the mathematical objects typically entering in physics computations. So, for example, if you go to the Wikipedia and search for Maxwell equations, you will find this table. In this table, you see abstract notation for coordinate-free representations for vectors, coordinate-free representation for the nabla differential operator as an upside-down triangle. You see the square representing the D'Alembertian already working in relativity theory. So this is tensor notation. They are contravariant, covariant indices. Maybe the space-time is curved, so the covariant, the non-covariant derivative becomes the covariant derivative, and this covariant derivative includes Christoffel symbols. This represents the square root of the determinant of the metric, and so on. And the computer algebra systems were not designed to compute with this kind of abstract notation with so dense mathematical contents behind. The situation is not different with regards to quantum mechanics, where the standard notation is direct notation. We compute with Ketz and Brass, representing, for instance, in an infinite dimensional case, representing these integrals. The product of a Bra and a Ket represents this integral from minus infinity to infinity. The mean value of an operator, where all these operators are non-commutative with respect to multiplication, in the case of a discrete basis, represents this sum, and so on. And we want to compute with the objects you see on the left-hand sides, but with them representing the contents you see on the right-hand sides. And again, computer algebra systems were not designed for this kind of notation originally. This situation is changing. We have implemented most of these things in the computer algebra worksheet in the Maple system. And so I want to illustrate a little bit both the abstract notation that is now available for algebraic computations in physics, and some of the problems that can be tackled with this notation. So I choose 5 examples, 1 in classical mechanics, 2 in quantum mechanics, and 2 in relativity, where my intention is not to go into the details about the physics, but just to illustrate the algebraic computations and the power of this more abstract and compact notation used in physics. So my first problem is to determine the inertia tensor of a 3-atomic molecule that has the form of an isosceles triangle with 2 masses in the extremes of the base and a different mass in the third vertex. The distance between the 2 masses M1 is equal to A, and the height of the triangle is equal to H. The context for this problem, well, this is a textbook problem taken from the Landau book for mechanics. So for the solution, we start with the general formula for the inertia tensor, and we already see these new objects where we see a vector. This is an algebraic vector, not a matrix. Is a coordinate-free representation for a vector, is the norm. This is the Kronecker delta symbol, and these are the components in the I and j directions of the kth vector, where k goes from 1 to n is the number of particles of the system, and m are the masses. These vectors are the position of the particles as seen from the center of masses. Okay, our problem has 3 particles. We create an indexing function to represent the inertia tensor as a matrix using this compact Maple notation, where we construct a matrix just using an indexing function. On the diagonal, we see the standard formulas for the components of the inertia tensor. Out of the diagonal, we see also the standard formulas related to each of the 3 directions, and so on. So in our problem, 2 masses are equal, and now we want to move away from the position vectors as seen from the center of mass to the position vectors as seen from an arbitrary system of reference. So the formula is that the position of each mass as seen from the center of mass is equal to the position of this mass as seen in an arbitrary system minus the position of the center of mass. So we choose the origin of this arbitrary system to be at the middle of the segment connecting the two atoms of equal mass. So the first atom is to the left, a distance a divided on 2. The second atom, same mass, is to the right. Again, the distance is a divided on 2. And the third atom is over the third vertex of the triangle at a distance h, is the height of the triangle. So the formula for the center of mass is this one. This is all standard. And because now all these vectors are defined, we can compute a value for the center of mass. So this is the position of the center of mass as seen from the arbitrarily chosen system of reference. We put the origin at the middle of the segment connecting the two atoms. So now we can compute these little vectors, which represent the position of each of the three atoms as seen from the center of mass, because these are the objects that enter the definition of the inertial tensor. So all the objects are defined, and therefore the little r1, r2, and r3 are given by this. And now all the objects are assigned, so we can directly compute the value of the inertia tensor by simply evaluating the matrix. So summarizing, we start with a very abstract formula for the inertia tensor, components of non-projected algebraic representations of coordinate-free vectors, coordinate-free representations. Then we have a matrix of somewhat abstract formulas, do few assignments, and we get the value. This illustrates well the kind of computation that can now be done with abstract vectors. Okay, going to something different. The first problem in quantum mechanics, I want to check that if two so-called conjugate variables satisfy a relation like this, that is, the commutator is equal to some constant, then the deviation with respect to the mean values of these conjugate variables, the product of the square of these mean deviations, has a lower bound, which is equal to h squared divided on 4. To show this, we start introducing Q and P as Hermitian operators, and the algebra rule that governs the problem, that is that the commutator of Q and P is equal to this. And then we introduce a basis of Ketz Psi. We will label it by Psi, and we will say that these Ketz are normalized to 1. And with this, we can already introduce the mean values of the operators Q and P as the brackets. And now we can introduce the deviations from these mean values. For that, we introduce another Hermitian operator, delta, which by definition, delta is equal to the deviation with respect to the mean value of the operator, in this case Q, in this case P. And interesting, because of the algebra rule already set, which is this, the deviations from the mean values automatically satisfy the same commutation rule. So the commutation for the objects on the left is equal to the commutation of the objects on the right. The commutator of the objects on the right is computed and is equal to this, and therefore we have another commutator relationship. We add this to the algebra rules in order to take this algebra rule at the time of simplifying. To find this lower bound for the product of the deviations with respect to the mean values, we define a Ketz Psi that involves the application of these deviations, delta Q and delta P, over an arbitrary any ket of the basis, and we introduce a parameter lambda. We will soon see the why. This parameter is real, and we now take the square of the norm of this ket, and we obtain this relationship. Now, here we see that there is the mean value of the product of delta q delta p, and here is the mean value of the product of delta p delta q. Of course, these objects don't commute, but their commutator is equal to the imaginary unit times the Planck's constant. So we can factor out the mean values and collect these two terms and apply the algebra rule. This is what the simplifier does, simplify with respect to the algebra rules, and obtain this relation. This is a polynomial of second degree in lambda, so its discriminant is negative or 0. So we compute the discriminant and we isolate h squared and immediately get the lower bound for the product of the deviations with respect to the mean values. Again, a rather abstract computation. It can now be performed in a natural way. Our second problem in quantum mechanics is the derivation of the field equations for a quantum system of identical particles. The background for this is that quantum systems of identical particles, if they are of boson kind, they enter a number of relevant problems nowadays, typically in the form of Bose-Einstein condensates. I will not go into details. In this moment, I'm just interested in computing the field equations for such a system. Okay, these equations are computed by constructing the Lagrangian and then minimizing the action by equating to 0 its functional derivative with respect to the field. So the first step is to introduce the energy density for a quantum system of identical particles. According to standard formulas, is given by this expression, where we see the norm of the gradient of C, we see the absolute value of C, V is an external potential, and this term is the atom-atom interaction. Between bars, we see the absolute value of the C field. We indicate the real objects of our problem, and now we construct the Lagrangian in terms of the energy using standard formulas again. So for this problem results in this Lagrangian, where we see the conjugate times the time derivative of C and the conjugate of that product, and so on. And now it's time to construct the action. The Lagrangian is just the integrand in a four-dimensional integral. And this is the functional derivative we want to take. So we want to variate C in form and apply this variation to this functional and get the terms up to first order. Here we are delaying the evaluation of the operation using quotes. And now we just perform the computation. And this is the result. It comes very rapidly. It's a complex operation to be done with paper and pencil. And it's essentially already the field equation for the problem. But for the fact that it's not entirely simplified, here we see three terms that can be collected together into the Laplacian, actually the conjugate of the Laplacian. So we introduce an inner form for this Laplacian. And now we substitute these three terms in the conjugate of that expression to obtain this. And now we just isolate the time derivative is here. So get this. And applying just some collection, we get the gross Pitayevsky equation in its standard form. Again, a simple computation nowadays on a computer algebra system, on a computer algebra worksheet, but a rather abstract if compared with the things that could be done a few years ago. And now I want to go into two examples from Relativity to make more complete the presentation. So the first example is to derive Maxwell equations in the tensorial form, departing from the four-dimensional action for electrodynamics. So for this, we first set a coordinate system. We define the four-dimensional electromagnetic potential. It's a tensor A mu. With it, we define the electromagnetic field tensor that enters the action for the problem. We define it the usual way as the antisymmetric combination of derivatives of the potential. And now we want to equate the zero, the functional derivative, where the integral in the action is actually the contracted form of the electromagnetic field tensor. So it's f mu nu squared. Again, we want to vary in form the potential A rho, and which means each of the tensorial components. There are these derivatives, the mu and the nu, and well, we want to perform the operation, and here it is. So this is the tensorial form of Maxwell equations, but for the fact that they are not really simplified. We see contracted indices. Here is mu, and here is nu and nu, here is nu and nu here. There is a D'Alembertian here, and there is a D'Alembertian here. So we want to simplify this expression with respect to the contracted indices, taking into account Einstein's sum for repeated indices. The simplifier of the physics package is this one, and here we are now with Maxwell equations in tensorial form. All nice, but where are the differential equations? Well, this is a tensorial expression, so let's compute the tensor components of this equation and convert the D'Alembertian, which is a second-order differential operator, to the standard diff Maple form, and here are Maxwell equations in standard Maple notation. To conclude, I want to talk about a problem in general relativity. It's a bit more complicated problem. This problem was presented to me a month ago by a Maple user who wanted to know how could he do this kind of computation on a computer algebra worksheet. So in his problem, the space-time metric is given by this expression. So it's a curved space, there is curvature, and he wants to compute the trace of this tensorial object where phi is some function of the radial coordinate, non-specified. R is the Ricci tensor. These, the alpha and the beta, are the covariant derivatives, so each of them has an extra term involving the Christoffel symbols. And this is the stress energy tensor given in his problem by this matrix. In second place, he wants to compute the traceless part of this expression. And in the third place, he wants to compute an exact solution to the nonlinear system of differential equations conformed by the components of the traceless part of Z. So first of all, the trace of Z, well, we set the coordinates. He worked in spherical coordinates. We introduced the line element for the space-time metric the way he indicated. With the line element, we just set the metric, and we can just check that the metric the covariant components are as he indicated, and indeed it is. They are. So now we introduce the energy tensor, the stress energy tensor. We define this to be a tensor so that we can compute with the components of this thing. And now we solve item A in one go. Just define a tensorial equation. We will call this Z. And define this so that we can compute with Z representing this so abstract tensorial equation where each object in turn is defined in terms of other tensors and other tensors. For instance, the Christoffel symbols are defined in terms of the space-time metric and so on. So to compute the trace, then we just write it is the contracted form of Z, and we sum over the repeated indices, and there we are, with a differential equation representing the trace of Z. Here, VRR, for instance, is the second derivative with respect to R. If we want to see this in the standard Maple notation, we just make it happen. Now, we want the components of double, the traceless part. Okay, this can also be solved in one step. By definition, the traceless part of Z is Z minus the trace of Z multiplied by the space-time metric divided the trace of the metric. So we define now double to be that tensorial equation in terms of tensors that are defined in terms of tensors that are defined in terms of tensors and so on. And then if we want the components of double, we just get all the components at once. It's very interesting how abstract is this computation and how rapidly it proceeds nowadays. Again, we have that the components form a system of differential equations, and in fact, this user asks for an exact solution for this system. So we first construct the system with the non-zero components of Dabo. We run a differential elimination process in order to see how many cases are behind. And indeed, there are 3 cases. So one is the general case, two are the singular cases. Two cases are singular. The first 2 cases involve rather large expressions, but the third one is small enough and can be tackled to the end. We see that the first equation is just a constraint between lambda and phi. Then there is one differential equation that is easy, one second differential equation which is second order nonlinear and coupled with phi, and then a simple first order linear equation for phi. So we first split into the constraint and the subsystem. We solve the differential equations. They happen to be solved in exact form. And now we use the constraint to connect one of the 3 constants that appear here. In fact, if we evaluate the constraint at this solution just computed, we see that there is a relation between C2 and C1. We solve for C1, and we substitute this into the solution just computed, and in that way, we get the solution to our original problem, or the system, which is the system conformed with the components of Dabo, which in turn is the traceless part of this expression for Z. We want to verify that this result is correct, and indeed, this solution cancels all the system. And that's it. Thank you for attending this presentation. I hope you enjoyed it. I look forward for taking your questions, if any. Thank you.
Hello, my name is Juergen Gerhard. I'm Director of Research at Maplesoft, and today I'm going to talk about research in polynomial computations. So this is the outline of my talk. I have 3 topics that I want to present. The first one is about fast and parallel polynomial arithmetic. Then I'm going to switch to parametric polynomial systems, and I'm going to conclude with something about differential algebraic equations. So let's start with parallel polynomial arithmetic. This is actually joint work that has been done with 2 collaborators from our research labs, Dr. Michael Monaghan and Roman Pierce at Simon Fraser University. The overall goal for the fast polynomial arithmetic project, and in particular here for fast polynomial multiplication, was drastic efficiency improvement of Maple's sparse polynomial arithmetic on both single and multi-core architectures. And this was achieved through 2 things. One of them is a new, very compact, sparse data structure for multivariate polynomials. And here's an example. So you can see these blocks. Each block is a machine word, and there are 2 types of blocks. The first block encodes the degree of the monomial. So for example, here we have the monomial x times y times z cubed. So that's represented by the numbers 1, 1, 3. And then another, you can think of it as a couple of bits of a machine word for the total degree. And then you have another machine word that encodes the coefficient. So this is a very compact data structure and very memory efficient. The other new ingredient is a heap-based algorithm that actually comes from merging, but is very useful here for sparse polynomial multiplication. So the individual products of the monomials are fed into the heap, are stored in the heap, and then are on the other side extracted and sorted. On the next slide, we see some benchmarks for this heap-based multiplication strategy for various versions of Maple. What you can see on the horizontal axis is the number of terms of the problem, and on the vertical axis the time. There's 2 series of benchmarks, one for dense polynomials and one for sparse polynomials. And you can see that over various releases, Maple has improved quite dramatically in the speed for both sparse and dense problems. The timings here are only until Maple 17, but there's going to be similar additional improvements in Maple 18 as well. Now I want to talk a little bit about the idea of parallelizing this. So instead of using just one heap, we're using a couple of different heaps, namely one thread per local heap. So basically one heap for each core, and then the input data gets blocked, and the various blocks get fed to the heaps in parallel. Then we have a second stage where the results from the local heaps are being merged by a global heap, and this global heap is actually not a separate thread, it is a task that gets shared among all the threads. So there's some load balancing happening here so that the global task gets carried out as well. So here are some benchmarks for the parallel multiplication. In Maple 17, again, we have at the top we have a series of dense benchmarks, and at the bottom we have some semi-sparse and very sparse benchmarks, and we're going up to 8 threads or 8 cores, and you can see that in the dense case for 8 cores, in the best case we achieve a speed up until up to 6, which is very good. The last slide on this topic is about some extensions and future work. So similar speedups were achieved for polynomial division and powering of polynomials as well, both in the sequential and the parallel case. And some ongoing and future work by those collaborators at Simon Fraser University is to look at parallelizing higher level polynomial operations such as greatest common divisors and factorization. And they're also looking at parallel sparse exact linear algebra, which can be used, for example, for Grübner basis computations. My next topic is about parametric polynomial systems. This is also joint work with a few collaborators from a university in France and from Western University. The motivation is we can handle problems that can be phrased as polynomial systems that have two kinds of indeterminates, the variables and the parameters, and every time I'm talking about a variable it's marked in blue, and when I'm talking about a parameter it's marked in red. Now for those kind of systems you will see an example below, for example the quadratic equation with parametric coefficients x squared plus ax plus b. Typical questions are the feasibility questions: for which values of the parameters do we have solutions for the variables, and this means in this context real solutions. And the next question is, if there are real solutions, can we get a formula that expresses the solution variables in terms of the parameters? So let's see what that means in this example for the quadratic equation. The feasibility: when does the quadratic equation have a solution? That's exactly when its discriminant is greater or equal to 0, so that's a squared minus 4b. And expressing the solution in terms of the parameters is this well-known formula for the general solutions of the quadratic equations. And those types of parametric polynomial equations problems appear frequently in applications. This is a list of the symbolic solution methods that are being employed in solving these kind of problems, either Grübner basis or triangularization based methods such as regular chains, cylindrical algebraic decomposition, and real root isolation as well. So I want to talk now about an application example from control theory. So what people in control theory consider is a feedback control system where we have a plant which has certain properties. It could be an engine, or it could be an electrical part, and we want to control it so that it has certain desired characteristics. Now in control theory, if the plant and the controller have linear behavior, then they're often represented by so-called transfer functions, and in our case parametric transfer functions. So on the right we have the parametric transfer function for the plant, which is just 1 over a polynomial of degree 3, and the controller is a so-called proportional integral controller which has 2 parameters a and b. And then one can, by standard transfer function operations, form the transfer function for the whole system, the feedback loop, and that is again a parametric transfer function which has a numerator polynomial of degree 1 and a denominator polynomial of degree 4, and both of them contain the parameters a and b. Now, one question that people in control theory are interested in is stability, and there's a well-known criterion going back to Hurwitz, which says that a transfer function is stable if and only if it does not have any poles in the right half of the complex plane. And these are poles in this Laplace variable S. So if we look at the original, the transfer function for the original plant, it is unstable. So on the right-hand side, you see a picture with the 3 poles of that transfer function. And there's one pole which is with an orange circle around it on the right, and that's an unstable pole in the right-hand side of the complex plane. And that's one of the reasons why people might want to control such a plant in order to make it stable. Now the question in this problem is, for which values of the parameters a and b is the controlled plant stable? And again, we have this transfer function for the controlled plant, and the Hurwitz criterion says that's the case if and only if there are no roots of this denominator with a positive real part. So if x and y are the real and imaginary parts of S, then that means for x greater than 0, there's no root of this denominator. If we put all this together, we arrive at the following parametric polynomial system. So we substitute S, we split up S into its real and imaginary parts, substitute that into the denominator of the transfer function. Again, take the real and imaginary parts. That gives us 2 equalities. So we're looking for roots, common roots of those first 2 equations, or we're interested in whether there are common roots for those first 2 equations where x is greater than 0 and the 2 parameters are positive as well. And the desired answer is actually that the system should not have any solutions. So if the system does not have any solutions, then the closed loop transfer function is stable. So the question we want to solve is, for which parameter values do we not have solutions? And this can be done with the root finding parametric package in Maple. So there's a command called cell decomposition. We just pass the system of equations and inequalities that we just saw on the previous slide to that command, and we say x and y are the variables and a and b are the parameters. That returns a record with a whole bunch of information, which I didn't print out here. And then the next command asks for which are the cells with solutions. So this record contains a decomposition of the parameter space, in this case the AB plane, into various cells. And in some of the cells the problem has a solution, and in other cells the problem does not have a solution. So here we're looking for all the cells where the problem does not have a solution, because those are the ones, because we formulated the problem in a little bit of a roundabout way, those are the ones that we're actually interested in. And then the third line, the cell plot command, will actually plot those solutions. And you can see here that we get this upside down parabola, which is cut off at the bottom. And that's basically the feasible region in parameter space. So for those parameter values that are in the green area of this plot, those are the ones that we're interested in, that those are good solutions for our parametric problem. To just verify that, we can take one of these feasible solutions, for example, a equals 2, b equals 10, plug that into the denominator of our closed loop transfer function, and find all the complex roots. And here we can see there it's a polynomial of degree 4, so there's 4 complex roots, and there's actually all of them are in the left hand of the complex plane. The last topic I want to talk about is about differential equations, and this is research work that has been done at Maplesoft. So what is a differential algebraic equation? It's like an ordinary differential equation plus some algebraic constraints, so constraints that do not contain any derivatives. And a typical example is a two-dimensional pendulum, where you can see the picture here on the right. So for the convenience of demonstrating this, the y-axis actually points downwards instead of upwards. And then we have 3 equations here, 2 differential equations for the x and the y coordinate of the pendulum. And we have one constraint equation at the bottom, which basically says that the mass at the bottom of the pendulum is attached to a rod of fixed length, which is again attached to a joint at the ceiling. And in order to formulate this, we also need an auxiliary variable lambda, which is often called a Lagrange multiplier. In order to be able to simulate such a system of differential equations numerically, for example in MapleSim, one needs to perform a process that is known as index reduction, which will convert the differential algebraic equations into ordinary differential equations. You can see the example here. Basically what happens is that the constraints are being differentiated, some solving happens, and some substitution of already solved equations into the newly obtained constraints. And if you do that a couple of times, then you arrive at this system of equations at the bottom, where we now have an explicit equation that expresses lambda in terms of the other variables x and y and their derivatives. So one particular way of doing index reduction is the projection method. This is a systematic approach based on geometry, which was originally introduced by Scott, Achevsky, and Blager for mechanical systems only. The main idea is to project the velocities in this example, so the derivatives of x and y, onto the constraint manifold. So the constraint manifold in this example is the unit circle x squared plus y squared equals 1. And the work that we did at Maplesoft here was to generalize this to not, from mechanical systems, to general types of differential equations in a special form called Hessenberg form. And you can see an example here at the bottom left. So basically Hessenberg form means it's triangularized. We have two types of differential equations, one that contain three types of variables, x, y, and z, one that contain only two types of variables, x and y, and the last one is not a differential equation at all. That's the system of constraint equations. And in addition, we also have some non-degeneracy conditions. So for the pendulum example, the pendulum originally was a second order system, so we have to rewrite it as a first order system. And then we see the y variables are the velocities u and v, the x variables are the position variables x and y, and the constraint is just the same constraint that we had in the previous example. Now, I don't have time to explain how the generalized projection method works in general, so I'm going to illustrate it using the example of the pendulum. So in the middle here, you see the equations that we start with for the pendulum. And on the right, you see just some naming. So the right-hand side here is what corresponds to f, g, and h in the generalized Hessenberg form. And these are the y, x, and z variables in the generalized Hessenberg form. So the first thing that happens is we take the gradient of the constraint equation. So there's a single constraint equation here, x squared plus y squared equals 1. We take the gradient, call that c, and then we compute an orthogonal complement of that gradient. So basically what we want is, this is a matrix C with the properties that C times D equals 0. Also, we introduce new velocity variables u that are tangential to the constraint manifold. So you can see that here in the picture, the velocity is basically tangent to this to the circle that the pendulum describes when it's swinging. So we're making this ansatz here. What you see on the left side of the new velocity variable u is exactly that matrix D from above. So the next step is we differentiate. So we take this new constraint equation that we have here, which does not contain any derivatives, and differentiate it with respect to time. Then we get this equation at the bottom, and there's also already some simplification happening by substituting in previous equations. Then this is where the projection method gets its name from. We should project by multiplying this newly generated equation from the left by the transpose of D. And that will lead to a considerable amount of simplification. So the coefficient at the very left, the coefficient of u prime, simplifies to 1. The coefficient of u squared actually simplifies to 0, and the right-hand side also simplifies. And what we see here is that this tangential velocity is basically proportional to the x-coordinate of where the pendulum is, and that's something that, with hindsight, makes a lot of sense physically if you think about the pendulum problem. So what have we achieved? We started out with 5 differential equations. Those are the 5 equations in the red box, and after application of the projection method, we are left with only 3 equations, and all of these are differential equations, so the constraint equations are gone completely. So that's a very useful simplification to have. For an outlook, what we did, we implemented this method in Maple, both the projection method itself, as well as the necessary reduction of a general type of differential algebraic equation to Hessenberg form before that, so that the projection method can be applied. We also looked at generalizations for higher index differential equations and for so-called mixed index differential equations. And an area for future research is to, one problem with this kind of approach, there's lots of symbolic matrices and matrix arithmetic occurring where the entries are symbolic expressions, and that immediately leads to expression swell, and that's a problem that we have some ideas for, but we haven't really looked into it yet. So that concludes my presentation, and I'm happy to take some questions. Thank you very much.
That concludes this session. Thank you for joining us today. Don't forget to visit the Communication Lounge to ask your questions. A recorded version of this presentation will be archived, and you will be notified when it's available.